Okay, everyone, in this video we're going to look at the fundamental theorem of algebra, what it means, what it helps us do, and kind of analyze things a little deeper. So, fundamental theorem of algebra, basically what this says is every polynomial that has a degree greater than 0 has at least one root in the set of complex numbers. And complex numbers are the real numbers, the imaginary numbers, when you put them together. So, anything that has a degree greater than 0 has at least one root. Okay? Basically, the big idea behind all of this is the number of zeros will always match the degree of the polynomial. Okay? So a zero, a root, a solution, kind of all the same thing. They're all the values where the function equals 0. Okay? Basically, it's just where the graph crosses the x-axis. So if I have a graph that does something like this, okay, you should notice that it has 1, 2, 3, 4 places that it would cross the x-axis, so it has 4 real solutions. Okay, and the real solutions are the ones that you can actually see. It may have some other ones, okay, which we'll talk about in a second, but it definitely has 4 solutions, so it is at minimum an x to the 4th type of problem. Okay, and we can look at this a little bit closer by something in these examples. It says, given a function, determine the number of zeros the function has. So the first one is 3x cubed minus 2x plus 7. Well, you go through this and you look for the degree. Now the degree, which we've talked about, is the highest exponent. Okay, and your highest exponent, as you notice here, is a cubed. So based on this, this is going to have 3 zeros. Now they may be real zeros, they may be imaginary zeros, but it has 3 zeros. Okay, that second one there. Negative 6x to the 5th plus 2x to the 4th minus 4x squared plus 3x plus 7 wants to know how many zeros does this have. So we look through this. It's got a 5, a 4, a 2, and a 1 as exponents. Well, the degree is the largest, and the largest is 5. So this has 5 zeros, and there you go. All right, so the question that comes up, and hopefully this is going to make some sense. The real roots are the places where the graph crosses the x-axis, like I said before. So what if you get a problem that's supposed to cross 5 times, but the graph is only crossed 3 times? Okay, so let's say I get this problem, and it's x to the 5th, blah, 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 whatever happens after that. But I look at the graph, and it does something like this. Notice there's only 3 places where that crosses. Well, this theorem says I have to have 5. What does that mean about the other 2? Well, remember I told you it could be complex. Complex means reals and imaginaries. So those other 2 are actually imaginary numbers. Okay, and we just can't see them on the graph. The last part of this is, given the following roots, find the quadratic polynomial that satisfies this. So they're telling you right now, my graph is crossed at 2 and negative 5. Okay, so if I were to graph this thing, here's 2. There is definitely a place there. Negative 5, there's definitely a place there. So I have a parabola that either looks like this, or it could even go this way, but it crosses at those 2 points. I want to know what's the equation for that parabola. Well, here's how you figure it out. It's pretty straightforward. In some of the problems we've done before, you've been given something like this and have been asked for the zeros. And remember, we take this, we set it equal to 0, we solve it out, we say the answer is 2. Or kind of in an easy shortcut, you just take the opposite of the number there. Well, what that would do is it would leave us with a 0 of 2. So if I'm told that the 2 is the 0, I can rewrite the factor as x minus 2. Now the same idea, if I'm told that negative 5 is the factor, I've got x minus negative 5 or x plus 5. And then from here, all we're going to do is we're going to FOIL this together. So I go through my FOIL process. Okay, so x times x is x squared. X times 5 is 5x. Negative 2 times x is a negative 2x. Negative 2 times 5 is a negative 10. Combine your like terms. You get x squared plus 3x minus 10. And there's the quadratic that actually satisfies that requirement. All right, the other option up there in this second example is 4i and negative 4i. Now the thing that you guys will start to notice as you go through these is the imaginaries must come in pairs. They have to come in pairs. All right, and I'm going to show you why here in a second. So setting this up the same way, if I have 4i, one of them is going to be x minus 4i. And then as I have a negative 4i, the other one's going to be x plus 4i. Okay, so they must come in pairs, and we've talked about it in some of the past sections when we looked at imaginaries. These are called conjugates because they have the opposite signs. Now, when I go through a FOIL, here's what happens. X times x is x squared. X times 4i is a positive 4ix. X times a negative 4i is the negative 4ix, and hopefully you guys see what's going to happen there. And then the last one is negative 4i times positive 4i, which is a negative 16i squared. Well, here's what happens. The 4ix and negative 4ix cancel. So I'm left with x squared minus 16i squared. And if you remember from the imaginary talk, I squared is negative 1. So that is replaced with a negative 1. Negative 16 times negative 1 is a positive 16. And there is my quadratic that holds those two zeros. Okay, so this is what you're going to be asked to do in this section, is to identify the number of zeros and create the quadratic polynomial that has the following zeros. Okay, if you need help, let me know.